Hello all, today we are going to discuss the superposition of waves. We know that a travelling wave moving along the positive x direction can be written as yx comma t is equal to a sine 2 pi by lambda x minus vt. That is the displacement of a travelling wave moving in a positive x direction. If we consider the superposition of waves, in order to consider the superposition of waves, we have to take two travelling waves of almost equal amplitude and slightly different wavelengths, lambda 1 and lambda 2. That is, take two travelling waves of almost the same amplitude A and slightly different wavelengths lambda 1 and lambda 2. That is y1 and y2. y1 and y2 are the two travelling waves. We superimpose these two travelling waves and we can represent y1 and y2 in terms of y in the form of y as y1 x comma t is equal to a sine 2 pi by lambda 1 x minus vt and y2 x comma t is equal to a sine 2 pi by lambda 2 x minus vt. Now we superimpose y1 and y2. So the resultant displacement will be y x comma t is equal to y1 x comma t plus y2 x comma t. Since both these waves y1 and y2 moves with the same velocity v, the resultant wave also moves without much change in its structure. So consider the resultant wave at t is equal to 0. At t is equal to 0, resultant wave will be y x comma 0 is equal to a sine 2 pi by lambda 1 x plus 2 pi by lambda 2 x. That is, we sum y1 and y2. So we get a sine 2 pi by lambda 1 x minus vt plus a sine 2 pi by lambda 2 x minus vt. That is y1 plus y2. So at t is equal to 0, this term will be absent. So we get a sine 2 pi x by lambda 1 plus a sine 2 pi x by lambda 2. A is common, so a take outside. So you will get a into bracket a sine 2 pi x by lambda 1 plus sine 2 pi x by lambda 2. This is in the form of sine a plus sine b. So use the relation sin a plus sin b is equal to 2 sin a plus b by 2 cos a minus b by 2. Here a is 2 pi x by lambda 1, b is 2 pi x by lambda 2. So what will be a plus b by 2? A plus b by 2 will be 2 pi x is common. So take it outside, 2 pi x into 1 by lambda 1 from this term plus b 1 by lambda 2. So 2 pi x 1 by lambda 1 plus 1 by lambda 2 divided by 2. That is the a plus b by 2 term. Similarly, a minus b by 2 will be 2 pi x 1 by lambda 1 minus 1 by lambda 2 divided by 2. That is the a minus b by 2 term. Substituting here, what will be the result? 2 sine. So here a is there. So the resultant will be a 2a sine. First term is sine a plus b by 2. 2 pi x 1 by lambda 1 plus 1 by lambda 2 divided by 2. This 2 and 2 will get cancelled. 2 and 2 will get cancelled. So the answer will be pi x into 1 by lambda 1 plus 1 by lambda 2. So 2 sine term becomes 2 into a. A is there, so 2a sine pi x 1 by lambda 1 plus 1 by lambda 2. Then cos a minus b by 2, that is cos pi x 1 by lambda 1 minus 1 by lambda 2. And so here we take two travelling waves having slightly different wavelengths lambda 1 and lambda 2. They can be represented as y1 and y2. Then we superimpose these two, that is y1 plus y2, and we get the resultant displacement of the wave, that is y. Y at the time t is equal to 0 we take, that is in this equation this term will get absent. So a sine 2 pi x by lambda 1 plus sine 2 pi x by lambda 2. sin A plus sin B form, that is 2 sin A plus B by 2 cos A minus B by 2. So the resultant will be 2 into A into first term sin A plus B by 2 becomes pi x 1 by lambda 1 plus 1 by lambda 2. Then cos A minus B by 2 becomes cos pi x 1 by lambda 1 minus 1 by lambda 2. So this is a pictorial representation of superposition of two travelling waves. This represents y1 with amplitude A, wavelength lambda 1 moves with velocity v, and this represents y2 with amplitude A, wavelength lambda 2 and velocity v, and the resultant wave will be like this. So from this expression we can found that the amplitude of the resultant wave becomes 2A, becomes doubled. So initially y1 and y2 have amplitudes A, but after superimposition what happens, the resultant travelling wave have amplitude 2A. So that is a resultant wave have doubled amplitude 2A, and the resultant wave will be looks like this, having amplitude 2A, varying wavelength. These two waves have constant wavelengths lambda 1. Here the constant wavelength is lambda 2, but in this case after superposition what happens, wavelength is not constant, that is it varies from 1 by lambda 1 plus 1 by lambda 2 to 1 by lambda 1 minus 1 by lambda 2. So there is not a so that is the wavelength is not a constant for this resultant travelling wave. Again, in the terms of wave number we can represent the resultant displacement as y is equal to, here we get y is equal to what, y is equal to 2 a sin 2 pi lambda 1 x plus sin 2 pi x by lambda 2. Here in terms of wave number we can represent it as 1 by lambda is wave number k, that is 1 by wavelength is equal to wave number. So this equation can be rewritten as, since k is equal to 1 by lambda, that equation can be rewritten as y is equal to a sin 2 pi k1 x plus sin 2 pi k2 x. Similarly this equation y is equal to a sin pi x 1 by lambda 1 plus 1 by lambda 2 cos pi x 1 by lambda 1 minus 1 by lambda 2 can be rewritten as in terms of k1 and k2, that is y is equal to 2a cos pi k1 minus k2 x sin 2 pi k1 plus k2 by 2 x. Now consider, let D be the distance between two successive zeros of amplitude, that is from this point to this point. Both these points displace the amplitude is 0. So consider the distance between two successive zeros of amplitudes as D. This distance is taken as D. Then the phase angle is pi x into k1 minus k2, and the phase angle becomes pi x into k1 minus k2 is equal to phi. When x is equal to d, means at this point, when x is equal to d, the phase angle covered becomes pi, that is from when the wave travels from x is equal to 0 to x is equal to d, at this point then what happens, the wave covers, what is this phase angle, this phase angle becomes pi, that is 180 degree. That is, consider the distance between two successive zeros of amplitude, that is this point and this point. These are the two successive points corresponding to zero amplitude, where the phase angle can be represented as pi x into k1 minus k2, that is taken as phi. When x is equal to d, this is x is equal to 0, this is x is equal to d. When x is equal to d, the phase angle covered is, this angle is 180, that is the phase angle covered becomes pi. Then phi can be written as pi. The phase angle covered becomes pi. Hence x is at x is equal to d, what is the expression for d? D becomes equal to, so from this equation phi becomes pi. at x is equal to d. So this pi and this pi gets cancelled. Then x is equal to 1 by k1 minus k2. At x is equal to d, x can be written as d. Then d is equal to 1 by k1 minus k2 is equal to, what is k1? 1 by, what is k1? 1 by lambda 1 minus k2 is 1 by lambda 2. Rearranging, we get lambda 1 lambda 2 by lambda 2 minus lambda 1. So we consider two points corresponding to 0 amplitude. X is equal to 0 and x is equal to d. X is equal to 0 means there is no phase angle, and x is equal to d, the phase angle covered is pi. That is, in this expression substitute pi for this phase angle phi, and this pi get cancelled. The expression for x becomes equal to 1 by k1 minus k2. At x is equal to d, d is equal to 1 by k1 minus k2. Rearrange in the form of wavelength, then d is equal to 1 lambda 2 divided by lambda 2 minus lambda 1. Now take lambda 1 as lambda and lambda 2 as lambda plus delta lambda. That is, if the wavelength are almost equal, then lambda 1 can be represented as lambda and lambda 2 can be represented as lambda plus delta lambda, where delta lambda is the small change in lambda. Then we can represent d can be approximated as d is approximately equal to lambda square divided by delta lambda. This means that a number of wavelengths given approximately by lambda by delta lambda is contained between successive zeros of the modulation envelope. That is, a number of wavelength given approximately by lambda by delta lambda is contained between successive zeros of modulation envelope. That is, this is the modulation envelope. This is the modulation envelope. This point to this point is represents the two successive zeros of amplitude, and in between these two successive zero amplitudes, and that is in this d length, what we get a number of wavelengths corresponding to approximately equal to lambda by delta lambda is obtained. In order to practically produce such a superimposed travelling waves can be done by superimposing two different frequencies and amplitudes of vibration simultaneously at one end of the string. So here we discuss the theoretical case. In practice, we can done this superimposition of travelling waves by superimposing two different frequencies and amplitudes of vibration. Two different frequencies and amplitudes of vibration. So in this theoretical case, we consider amplitude is almost the same but with a slightly varying wavelength. In practice, we have to consider the travelling waves of different frequencies and amplitudes in order to get the superimposed wave. So first we consider the situation. So in order to get the superimposed solution, we get the situation x is equal to 0. Then yx comma t can be represented as y0 comma t is equal to a sine 2 pi by lambda 1. X becomes 0, that is 0 minus vt plus sine 2 pi by lambda 2, 0 minus vt. This is sine minus theta. Sine minus theta is minus sine theta. So y0 comma t is equal to minus a sine, minus take outside from these two terms, these two sine terms. So the answer will be minus a bracket sine 2 pi by lambda 1 vt plus sine 2 pi by lambda 2 vt. Put 2 pi v by lambda 1 as omega 1 and 2 pi v by lambda 2 is omega 2. Then y0 comma t is equal to minus a sine omega 1 t plus sine omega 2 t. Here also this equation is in the form of sin a plus sin b. Use the relation sin a plus sin b is equal to 2 sin a plus b by 2 cos a minus b by 2. So what will be the result? y0 comma t is equal to 2. So 2 into minus a, that is minus 2a into sin a plus b by 2 becomes sin omega 1 plus omega 2 by 2 into t plus, so there is not plus, there is no plus in this expression. It is a mistake from my side, please ignore it. The resultant wave is y0 comma t is equal to minus 2a sin omega 1 plus omega 2 by 2 into t cos omega 1 minus omega 2 by 2 into t. So this is the final expression we obtained for the superimposed wave. Here minus 2a cos omega 1 minus omega 2 by 2 into t represents the amplitude of the resultant wave. So in practice we considered two waves of different frequencies and amplitudes and we superimpose the wave, and the resultant wave will be get in this form. We have already discussed this form before. In this equation, consider the situation x is equal to 0. That is, in practical, we consider the superimposition at one end of the string. That one end of the string is x is equal to 0. It is the one end of the string. So here we substitute 0 for this x value, and we get y0 comma t is equal to minus sin 2 pi by lambda 1 vt plus sin 2 pi by lambda 2 vt. We use the relation sin a plus sin b. We end up with this equation minus 2a sin omega 1 plus omega 2 by 2 into t cos omega 1 minus omega 2 by 2 into t, where minus 2a cos omega 1 minus omega 2 by 2 into t represents the amplitude of the resultant wave. So now we consider the special cases when the resultant amplitude is maximum. What is the situation when the resultant amplitude is maximum? Resultant amplitude maximum means this cos term will have maximum value. Maximum value means plus or minus 1. So when the resultant amplitude is maximum, cos omega 1 minus omega by 2 into t is equal to plus or minus 1, which means that omega 1 minus omega by 2 into t is equal to n pi. Cos theta is maximum and theta is equal to n pi. So omega 1 minus omega 2 by 2 into t is equal to n pi, where n is equal to 0, 1, 2, etc. Equating these two, we get t now represent omega in terms of nu, that is 2 pi into nu1 minus nu2 by 2 into t is equal to n pi. From that, t can be represented as t is equal to n by nu1 minus nu2. Now substitute the values for n here, n 0, 1, 2, etc. So first value is n is equal to 0, then t is equal to 0. The next value n is equal to 1, then t becomes 1 by nu1 minus nu2. The next value will n is equal to 2, then t becomes equal to 2 by nu1 minus nu2, etc. So the values of t will be t is equal to 0, 1 by nu1 minus nu2, 2 by nu1 minus nu2, next is 3 by nu1 minus nu2, like that it goes on. Now the time interval between two successive maxima will be, what is the time interval between successive maxima? This 1 by nu1 minus nu2 minus 0, 1 by nu1 minus nu2. Take these two, 2 by nu1 minus nu2 minus 1 by nu1 minus nu2. Again we will end up with 1 by nu1 minus nu2. So the time interval between two successive maxima is 1 by nu1 minus nu2. This is the case when the resultant amplitude is maximum. Now consider the second case where the resultant amplitude is minimum. Resultant amplitude is minimum means cos this term becomes 0. That is the minimum amplitude. Cos omega 1 minus omega 2 by 2 into t is equal to 0 means omega 1 minus omega 2 by 2 into t is equal to 2n plus 1 pi by 2, where n is equal to 0, 1, 2, etc. In terms of nu, we can represent this equation as 2 pi nu1 minus nu2 by 2 into t is equal to 2n plus 1 pi by 2. Equating, we get t is equal to 2 get cancelled, pi get cancelled. So what will be the equation? 2n plus 1 divided by 2 into nu1 minus nu2. substitute the values for n, that is 0, 1, 2, etc. Then we will get t as t is equal to, first case n is equal to 0. The equation expression for t becomes 1 by n is equal to 0, then 1 by 2 into nu1 minus nu2. Next case n is equal to 1, so 2 into 1 plus 1, that is 3 divided by nu1 minus nu2. Next case n is equal to 2 into 2 plus 1, that is 5 divided by 2 into nu1 minus nu2. Next case will be 2 into 3 plus 1, that is 7 divided by 2 into nu1 minus nu2, and like that it goes on. Now what is the time interval between two successive minima? That is 3 by 2 into nu1 minus nu2 minus 1 by 2 into nu1 minus nu2. Here also we get this time interval as 1 by nu1 minus nu2. So both these cases, when the resultant amplitude is maximum and when the resultant amplitude is minimum, we get the time interval between two successive maxima and minima as 1 by nu1 minus nu2. Time interval between two successive maxima and minima means, that is the time period. That is, time period is 1 by nu1 minus nu2. Time period means a number of beats formed per second. That is frequency. Time period means 1 by nu1 minus nu2. Then frequency will be nu1 minus nu2. That is, number of beats formed per second. Number of vibrations or number of beats produced per second will be equal to nu1 minus nu2. So here we get the expression for the superimposed wave, where minus 2a cos term represents the amplitude. Here we consider the two situations. One is resultant amplitude is maximum case, next is resultant amplitude is minimum case. Both these situations we find out the expression for t, that is the time for this vibration. T is equal to, for maxima we obtain the expression as t is equal to n by nu1 minus nu2. For minimum amplitude we get t is equal to 2n plus 1, 2 into nu1 minus nu2, and both the cases we get the time interval between two successive maxima or two successive minima as 1 by nu1 minus nu2. Time interval between two successive maxima and minima means the time period, that is, time period is 1 by nu1 minus nu2. Time period is 1 by nu1 minus nu2 means frequency is 1 minus nu1 minus nu2. That is, the number of beats or vibrations formed per second is nu1 minus nu2. These are some of the results of the superimposition of waves in the case of certain musical instruments. Practically, mainly we obtain the good results for superimposition in the case of sound waves. Sound waves shows the better results for superimposition, and these are some of the waveforms of certain musical instruments like flute, clarinet, oboe and saxophone. These are some of the practical examples. All these figures represents the superimposition of sound waves. That is, there will be an instrument that is act as a source, and there will be a detector to collect the sound from this source, and at this detector we get the superimposed wave. That is, the sound waves produced from this music instruments get superimposed, and this superimposed wave is detected by a detector, and this the results obtained from the detector is shown here. These are some of the results of certain music instruments. Mainly sound waves shows better results for superimposition. That's why they gives the results for music instruments. Okay, I hope you understand today's class. Today we discuss the superimposition of waves. First we represent the theoretical formulation of the superimposition of two traveling waves. Then we move on to the practical case, that is, in practical how we can generate the superimposed wave. Then we consider the for practice we have to consider varying amplitude and frequency traveling waves for superimposition, and we consider the superimposition of these waves at one end of the string, that is at x is equal to 0, and we get the final expression for the superimposed wave. Then we consider the special cases, that is when the amplitude of the superimposed wave is maximum and when the resultant amplitude is minimum. So we have already discussed that this is the expression for the superimposed wave. There is a maximum amplitude and there is a minimum. This point corresponds minimum amplitude, this corresponds maximum amplitude. So then we find out, so here we find out the expressions for what will be the time obtained when the amplitude is maximum and minimum. We find the expressions, and we found that the time interval between two successive maxima is same as that of the time interval between two successive minima. Hence the frequency will be equal to nu1 minus nu2, or the number of vibrations or beats produced per second will be nu1 minus nu2 for both maximum amplitude and minimum amplitude. And we discuss some of the practical obtained results of certain music instruments. Okay, I hope you understand today's class. Thank you.